What is going on, everybody? Welcome to the fourth machine learning and third regression tutorial. Where we left off, we had defined or at least figured out what our features and our labels were. We haven't quite yet defined them, but in this one, we're going to define them. We're going to actually pass them through to a classifier, train and test that classifier to see how we do. So before we get started, let's go ahead and make some new imports. Also, I'm just going to put Quandle and math on the same line. Now we're going to go ahead and import NumPy as NP. NumPy is just a nice computing library. It's going to allow us to use arrays. Python doesn't actually have arrays, but NumPy will let us do that. Also, from Scikit-Learn, we're going to import pre-processing. This gives us quite a few things, but we're actually going to be using the scaling. Scaling your data is usually done on the features, and the goal is often to get your features to be somewhere between -1 and a +1. This can just help with accuracy as well as just processing speed or how long it might take to actually do the calculations. When we get there, I'll explain why you may actually just either choose not to do pre-processing, or maybe it's just too tedious to incorporate it in reality. But anyway, I'll show it because it exists and it can be useful. Next is cross-validation. We're going to use cross-validation to create our training and testing samples. It's just a really nice way to split up your data into, it'll shuffle your data for you, which helps with statistics basically, so you don't have a biased sample. And then also it helps separate your data. It's just a nice time saver basically. And we're also going to bring in SVM. That we're not to the support vector machine part, and I'm not going to explain support vector machines just yet. We will get there, but you can use an SVM to do regression, and we are probably not going to come back to regression, so we'll just show it as an example using it. Also, it's useful because I'll show you how freaking simple it is to change the algorithm that you're using. So anyways, SVM. Next, we're actually going to bring in regression. So from Scikit-Learn .linear underscore model, import linear regression. Okay, now we are ready to rumble. So the first thing that we're going to go ahead and do is define our X and Y. So generally, features and labels are defined. Features will be a capital X, labels will be a lowercase y. X is going to be equal to NumPy array of df.drop, and we're going to drop the label column, right? So your features are basically everything except for the label column, and we can do this because df.drop returns a new data frame. So it's returning a new data frame, it's being converted to a NumPy array, and it's being saved to the value of X. Now, the value of Y is our labels, so you might be able to surmise that we're just going to say np.array df label. Easy enough. Okay, so now we're going to scale X. So X equals pre-processing.scale X. Okay, now think about it. So here, we're scaling X before we feed it through the classifier. But let's say we feed it through a classifier, we have a classifier, and then we're using it in real time on real data. Well, let's say you're reading in that data and you feed it through your classifier, but before you do that, you really have to have scaled it. And to scale it, it's all scaled together, so it's like normalized with all the other data points. So in order to properly scale it, you would have to include it with your training data. So keep that in mind. If you ever go into the future and you're actually using this, you need to scale the new values, but not just scale them, but scale them alongside all your other values. So this can while it can help with the training and testing, it can actually add to processing time, especially if you're doing like any sort of, like, for example, with here we're using stock prices. If you were doing like high frequency trading, you would almost certainly skip this step. But anyway, there's that. Now we're going to redefine X as being equal to X to the point of where we were able to forecast underscore out plus 1. So this it includes all the points, because remember we shifted to, this 0.01 so this like what, 1% basically. So we made that shift. So we just want to make sure that we only have x's where we have values for y. And so we do that, and then we're going to say df.dropNA in place equals true, and then we're going to define y as equal to np array df label, and let's go ahead and let's print len of x and then len of y. So just make sure we have the correct lengths here. Right, so we don't have the correct lengths. So let's close this. And really, probably at this point, so we actually may not need to have this. Let me rerun that real quick. So I'm thinking, yeah. Okay, so because we won't have a label for the reason why I was doing this shift initially was because we wouldn't actually have labels, but we dropped those labels here, or those rows here. So we didn't need to do what we were doing there. So okay, so we've got our x's and our y's, and we don't need this, hopefully. Okay, so now what we're ready to do is create our training and testing sets. So we're going to say x underscore train, x underscore test, y underscore train, y underscore test equals cross validation dot train underscore test underscore split. And what you're going to pass through here is the x's, the y's, and then how big of a test size do you want? And we're going to do 0.2, so 20% of the data we want to actually use as testing data. So again, what this is going to do is it's going to take all our features and our labels, remember kind of the order, it's going to shuffle them up, right, keeping x's and y's connected, right, so it's not going to shuffle them up to the point where you lose accuracy. So it shuffles them up, and then it outputs for x training data, y training data, x testing data, and y testing data. So x train and y train we use to fit our classifier. So let's do that next. So first we're going to need to define a classifier. So we're going to say classifier equals, and we'll use linear regression to start. And then to fit or train a classifier, just clf.fit, and you fit features and labels. So which ones should we use? Well, we would use the x train and y train. Now we've got our classifier. We could actually use this classifier to predict into the future, do all kinds of crazy stuff. But first, we probably should test it, right? See what our accuracy is. So now what we would say is clf.score. So fit is synonymous with train. Score is synonymous with test. So we'll use x test, y test. So real quick, why might you want to train and test on separate data? Well, if you train a classifier to predict based on the same data that you test against, when you go to test it, it's going to be like, I've already seen this information, so I know exactly what the answer is, right? So that's not good. You don't want to do that. It's no different than if you were in school or whatever, and the same questions that you were asked in class were the exact identical questions on a test, right? If you missed those, then you just weren't paying attention or something. So here we have our score, and what we're going to say is confidence equals clf.score. You could also maybe replace confidence with accuracy. Accuracy. And that's probably a better choice because confident, you can kind of get two values, not necessarily from this one, but as we go into the future, you can actually compute both accuracy and confidence as two different values. So we'll go ahead and keep accuracy there, and let's print accuracy. So let's save and run that. Wait for it. And the accuracy that we got out of this is 0.96. So 96% accuracy on predicting what the price would be shifted 1% of the days. So this would be, let's go ahead and print forecast out just so we can see what that value actually is. So with linear regression, just so you know, the accuracy is going to be the squared error, and we'll talk about that coming up next as we break down how linear regression actually works. So this is actually still 30 days in advance. So it's pretty interesting that you'd still be that accurate, but okay. So now, what if though, a couple things. First of all, it's squared error. So this actual percentage of accuracy is not necessarily like you would get rich off this algorithm. It's almost like maybe directionally accurate, but that's pretty darn accurate. So let's say though, remember we also brought in SVM. Let's say we wanted to use the support vector regression, which is not simple linear regression. So we're not going to actually break down. But what if we wanted to use a different algorithm? So we're using linear regression. Here's how easy it is to switch your algorithm. svm.svr. Done. So now we're testing a new algorithm. And this one does actually a lot worse. Wow. Let's run that one more time. Let's see if it's still as inaccurate. Yeah. Wow. That's an interesting, that's a huge difference. Anyway, you'll actually kind of find that happens. Now, for example, with machine learning, like with support vector regression, for example, you have these things called kernels. So you might say kernel equals, I want to say the default is linear. So let's try polynomial kernel. So you can change these kernels in there and you can kind of fiddle with it and see if you could get better values. Oh my gosh. So 51% accuracy is like just barely better than average, or barely better than like a coin toss. Let's see if we can actually get under 50. No. Wow, that's a significant variance. My goodness. Anyway, as we can see, support vector regression is not what we're going to be using in this case anyways. But so here's another decent example about why you'd want to follow this tutorial series though. Like, what's a kernel, right? So we'll be explaining what a kernel is when we get to support vector machines. But anyway, what this was meant to show is how easy it is to switch between algorithms. And this is the case whether you're doing regression or whether you're doing classification or clustering. You can switch algorithms really quick. So you definitely want to like test the algorithms. Whoops, we did svm.linear regression. Okay, so anyways, there's that. One more thing to talk about before I let you guys go is with the various algorithms, you'll want to check the documentation. So let me pull up the documentation for linear regression, for example. And what you're looking for is which algorithms can be threaded. So in this case, we are looking for n_jobs. The question is, how many jobs can we perform at any given time? And so right now, it may not be totally obvious to you why with, let's say, linear regression, we can thread the heck out of linear regression as opposed to a support vector machine where there are ways that you could do it. You could like do it in batches or something. There are ways that you could do it, but it's just not inherently as easy as something like regression is to thread it massively and run it in huge parallel operations. But with regression, it totally is, and you'll see why later on. But anyway, so yeah, so this is just so if you were following along and let's say you're skipping the true breakdowns, shame on you. But to find out if really quickly if the algorithm could be threaded, you would just go to the page, right? You could just search linear regression support vector machine on Google. You'd find yourself on this page, and you're looking for n jobs. So this just means how many jobs, how many threads are we willing to run at any given time? So the default, let me think here. So the default for regression is actually 1. So this means it's running in, I hate to use the word linear here, but it is running linearly, right? Whereas we could run it in parallel by doing n jobs equals, and you could say, okay, I want to run at least 10 jobs at a time. So that'll run 10 jobs at a time. And in theory, the training and testing part, or actually, I'm sorry, just the training part would be significantly faster. Or you can use -1, and this will just run as many jobs as possible by your processor. So anyway, speaking of which, processor-wise, as you follow along this series, if you get to a point where like I'm getting it really fast and you're going really slow, like if you're following on like an older computer or a laptop or something like that, it may take you a little longer to run some of these things. This one should be pretty quick, but it's conceivable, especially when we get into like deep learning. You might want to think about spinning up a server or something like that, but that's obviously way down the line. We'll talk about it when we get there, I suppose, but just keep that in mind. So anyways, just remember this, but then again, just one more plug about why you'd want to dig in deep, which we're about to be doing, is to understand which algorithms you can do this with. So for example, with deep learning, like linear regression, not just in deep learning, like all the algorithms really, there's a lot of like linear algebra that goes in, because a lot of these things can be super threaded and you can run many operations at once. And like, so as we grow in processing power, that becomes very useful to have calculations and methodologies that can scale like that. Anyway, that's it. Here in the next tutorial, we're going to be talking about predictions into the future using Scikit-Learn, and then after that we're actually going to be breaking down linear regression and doing it ourselves. So stay tuned for that. If you have questions, comments, concerns, whatever up to this point, feel free to leave them below. Otherwise, as always, thanks for watching, thanks for all the support and subscriptions, and until next time.